So the voltage of a sine wave can also be specified as either a peak to peak or RMS value. RMS means root mean square value. So the peak to peak is at twice of the peak value. Since it is a symmetric waveform, symmetric about to x-axis, symmetric about x-axis. X-axis avatala paina kinda kuda same okay equal ga undi kabatti this sinusoidal waveform generally is called as a symmetric about x-axis, and it is a periodic. Periodic means what? The same sort of cycle is repeated, right? So for that one, the peak to peak value, that is positive peak here is, and this area is the negative peak. And from positive peak to negative peak, the magnitude, the negative peak may be a minus 20 volts, doesn't matter. And the positive peak may be a 20 volts here. Both are same, but in the opposite sign. And the peak to peak value, if you want to find out, you have to find out the peak to peak value is given by 20 minus of 20 or 20 plus 20. We can say it is around 40 volts. And the RMS value of this voltage is this is one, right? What is RMS value and all we will discuss in due course, right? Then angular measurement. Angular measurement can be made in degrees or radians in case of a sinusoidal waveform. The radians is the angle that is formed when the arc is equal to the radius of the circle. Right. When this arc we have developed is equal to the radius of this. See here, this one is the radius of a circle. Right. So now there are 360 degrees or 2 pi radians. So if you want to represent a sinusoidal waveform, the sinusoidal waveform you write it 0 to 360 degrees for one cycle. Or in terms of radians, if you want to represent it, you can represent it as 2 pi radians. So 2 pi radians is here. So pi radians is here. That is pi radians is equal to 180 degrees. So angular, because of here, there are 2 pi radians in one complete revolution and 360 degrees in one revolution of your sinusoidal waveform. The conversion between the radians and degrees is easy to write. To find the number of radians given the number of degrees is given by radians is equal to 2 pi by 360 into degrees. So if you want to convert a quantity in degrees into a radians, equivalent radians, that is 2 pi by 360 into degrees. So then you will get the radians of that quantity. And if you want to find out the degrees of that quantity from radians, then the formula is simple, right? The degrees is equal to 360 by 2 pi into radians. So now you please keep it in mind that while you are utilizing the calculator, so this 2 pi indicates is radians, it is in radians, right? This 360 should be in the degrees only, right? Now, the next one is the instantaneous values. The instantaneous value of a wave are shown as V or I. So, in case of a sinusoidal voltage, generally, and another important term apart from the angular positions and all, or peak to peak value, right, or maximum value, right. One more important term which generally we use here it is instantaneous value, and that is generally represented. Suppose if it is a voltage waveform, you represent it with V, and if it is a current waveform, you represent it with I. And you must be very careful while you are using the notations, right? In case of instantaneous values of a sinusoidal waveform or any waveform, we use generally with lowercase letters. Instantaneous values always with represent with lowercase letters and small v, small v, and small I. So general instantaneous values. So the instantaneous values are generally represented with small letters like this. Right. So the equation for the instantaneous voltage V of the sinusoidal waveform is represented as generally is V is equal to Vp sin theta, where Vp is the capital letter which I used is for the peak voltage or peak value, and theta is the angle in radians or in maybe in degrees. And some other form of the sinusoidal expression is V is equal to Vm sin omega t. So this is also used here instead of theta. So sometimes we also use here omega t, where omega t is where t is the time. This is directly given in radians. This theta is directly actually is given in either in radians or in degrees. Whereas if we use this expression v is equal to vm sin omega t, that t is the time, and when t is used as a time, then this omega should be equal is a radians per second. It must be in radians since t is in seconds. Therefore, if you right. So if you multiply omega with t, that what will get radians only. Once again, you will get the angle, right? This is your angle one. And Vm is the maximum amplitude. We call Vm or peak value also we call this as a maximum value or peak value, right? So sometimes we use this type of notation. Sometimes we use this type of notation. Nothing wrong in that. All these notations are same, right? So now in this example, if the peak voltage is C, if the peak voltage is 25 volts, if peak voltage is 20 volt, the instantaneous voltage at 50 degree AC is given by 19.2 volts. That is, you substitute Vp is equal to 25 here and sine of 50, then 25 into sine of 50 will give you 19.2 volts. Therefore, the instantaneous value of voltage for the given instant of that is given instant at 50 degrees. So at 50 degrees, the voltage will be 19.2 volts. This is the meaning of this example, right? Now, a plot of this example previously slide, which we have shown, the peak value is here. Let us think the peak value which we have already discussed in the previous example is 25 volts. All right, and 50 degrees, as I mentioned earlier. So 50 degrees means, so your waveform is starting at 0 degrees, and this is at 360 degrees, and this point is at 180 degrees. Now we want to find out the value of instantaneous value of voltage at V of 50 degrees. That V of 50 degrees is nothing but Vp is 25, so 25 into sine of 50 degrees. So that is we got it is around 19.2 volts, and you look at that graphically. Yeah, at 50 degrees, this is the 50 degrees. ఈ పాజిటివ్ ఆబ్స్టికల్ ఎంత 180 లో సగం 180లో సగం ఎంత అంటే it is 90 degrees around, and this would be 50 degrees. At 50 degrees, see here, at 50 degrees the value of the voltage here is given by 19.2 volts, right? So this is how the pictorially we represent the waves. Then coming to the next term, important term here, it is phase shift. The phase of a sine wave is an angular measurement that specifies the position of a sine wave relative to reference. To show that a sine wave is shifted to the left or right of this reference, a term is added to the equation given previously. Ante the phase of a sinusoidal waveform is nothing but an angular measurement that specifies the position of the sine wave. Sine wave ekkadundo cheppedi aa angular measurement ne manam phasor antam. Now let us look at this. Yeah, suppose you take a sinusoidal waveform like this, and if your sinusoidal waveform is now it is starting here, let it be. All right, this is 5. That is actually your we expect every sinusoidal waveform is will start at 0 reference. So that is of the reference which we have quoted here. See here. So the reference generally we start here. This is maybe the reference. Now, if you look at the sinusoidal waveform, so what is the position of the sinusoidal waveform? The angular measurement you find out here. This measurement is called as 5. And now, if your sinusoidal waveform is starting at this point, right? That means 0 degrees after 0 degrees, and at a point of 5 degrees it is starting. So that represent the sinusoidal waveform. How do we represent it? That we call as a phase shift. Therefore, V is equal to Vp sine of theta. This original expression is theta, and since it is a lag of 5 angle, and that is why it is being represented with minus sign here, or plus sign. Plus sign ఎప్పుడు వస్తుంది అని అంటే ప్లస్ సైన్ ఈ సపోజ్ ఇక్కడ వస్తుంది, అది నెక్స్ట్ స్లైడ్ లో చూపిస్తాను, రైట్? దిస్ వి కాల్డ్ as the phase shift, right? See, look at this diagram. So now in this diagram there are two waveforms. There are two waveforms. We have one is represented in red, another one is represented in blue. Yeah, but both are sinusoidal waveforms only. Basically they're sinusoidal waveforms, right? But they have a phase difference or phase shift or the angular measurement. If you look at that, the first phase, see here, this is the actual the first waveform which is starting at 0. Therefore we treat that this is a reference waveform or the reference point. Now if you look at the second waveform here, and the second waveform is starting after 45 degrees from 0 నుంచి 45 degrees, దీన్నే మనం phi అన్నాం. So now how do you represent this second waveform mathematically? Here is given by V is equal to 30 volts into sine of theta minus 45 degrees. Why? Because why minus sign I already told you, after 0 degrees, that is after reference, 0 reference, it is starting here, right? ఇక్కడ 45 degrees దగ్గర నుంచి అక్కడ 0 అయింది. ఈ వేవ్‌ఫార్మ్ 0 ఎక్కడ ఉంది? ఇక్కడ ఉంది. యాక్చువల్‌గా రిఫరెన్స్ వేవ్‌ఫార్మ్ 0 ఎక్కడ ఉంది? ఇక్కడ ఉంది. అంటే దిస్ వేవ్‌ఫార్మ్ ఈస్ బిహైండ్ దిస్ వేవ్‌ఫార్మ్. డు యూ అగ్రీ విత్ దిస్ ఆర్ నాట్? సో ఇఫ్ యూ లుక్ at these two waveforms are on the same graph, but one waveform is ahead of another waveform. So it is just like a two persons running on a track. Suppose if you have two person, a person one is running here, this is the person one, and the person two is here. So both are running in the same direction here, right? But they have been displaced by some distance, and this distance here in this way we have represented as it is 45 degrees. ఇక్కడ డిస్టెన్స్ మనం జనరల్ గా లీనియర్ అయితే, లీనియర్ స్కేల్ మీద అయితే మనం డిగ్రీస్ లో చెప్పాం. ఇది ఏంటంటే యాంగులర్ స్కేల్ కాబట్టి మనం డిగ్రీస్ లో చెప్తున్నాం. అంటే దీని నుంచి దిస్ ఇస్ పర్సన్ 1. సో పర్సన్ 1 ఈస్ హియర్ అండ్ వేరస్ పర్సన్ 2 ఈస్ హియర్, రైట్? యూ కెన్ సే పర్సన్ 1 ఈస్ హియర్ అండ్ పర్సన్ 2 ఈస్ హియర్. So can I say person 2 is behind person 1? Obviously. Why? Because he is always behind the person 1. And with which distance? 45 degrees always. Because both are running with the same speed. ఇప్పుడు ఇద్దరు కూడా ఒకే స్పీడ్ తో తిరుగుతున్నారు. కానీ ఏంటంటే ది పర్సన్ 1 is starting here, whereas the person 2 is starting here. ఈ ఇక్కడ నుంచి అంటే పర్సన్ 1 కి వెనకాల నుంచి స్టార్ట్ అవుతున్నాడు కాబట్టి, and that expression we have shown with a negative sign. See, and has that is why this equation has a negative sign, because there will be a negative phase shift we have, right? So దీన్నే lagging అని కూడా అంటారు. Lagging behind, generally we always use this term. So now what we can say is the equation 2, that is the sinusoidal waveform red is lagging the sinusoidal waveform 1 with an angle of minus 45 degrees. So the term lagging generally we use when there is a negative phase shift is appears in the sinusoidal expression. Right. So this is how. Then suppose if the person is leading, suppose if person one is here, for example, if person one is here, right, and a person two is here, right. So the person one is here right now, that is blue, and person two is here, and both having a distance of 45 degrees. That is, we can say person two is leading. He is leading. Enduku he is before the person one. Therefore, similarly, if the waveform is before that, then we can say it is leading. Right. See this example. అది ఇక్కడ మనకి క్లియర్ గా తెలుస్తుంది చూడండి ఈ ఎగ్జాంపుల్ లో. Now the waveform 2 here, this is waveform 2 and this is a waveform 1, whereas waveform 1 is always starting from 0, but waveform 1, sorry 2 is started at minus 45 degrees. Though they are started at minus 45 degrees, అంటే 0 కన్నా ముందరే స్టార్ట్ అయ్యాడు. అంటే a person is already started before first person. The second person is always started before first person and he always leads the first person. Therefore, that leading phase shift or the positive phase shift is represented in the form like this. So V is equal to 30 sin theta plus 45 degrees. This holds good. Please keep it in mind. This holds good. Both the equations are same. అంటే రెండు కూడా ఒకే రెండు వేవ్ ఫార్మ్స్ కూడా ఒకే స్పీడ్ తో తిరుగుతాయి. ఒకే స్పీడ్ అంటే ఏమిటి? ఒకే యాంగులర్ వెలాసిటీ. అంటే సపోజ్ ఇఫ్ ఐ సే V1 is equal to 30 sin theta అని రాస్తే V2 should be also be 30 sin theta plus 45 degrees. అంటే ఈ రెండిట్లోనూ డిఫరెన్స్ ఏమిటి? ఓన్లీ 45 degrees. This 45 degrees plus 45 degrees we call it as the phase shift. Because both are having theta same angular displacement. సో రెండిటికి theta is common. ఇది ఎప్పుడు theta కామన్ గా ఉంటేనే మనం ఇలా చెప్పగలం. అప్పుడు ఏమంటాం? V2 is leading V1. This one we can say V2 is leading V1. This will holds good only when both the expressions contain the same angular velocity theta, either in omega t or in theta, whatever it is. అలా కాకుండా suppose if V1 is in theta, V1 is in theta and V2 is if it is in some other expression 30 sin theta 2 plus 45 degrees, then we cannot compare these two because దీనికి ఇది theta అది theta లో ఉంది, theta 2 లో ఉంది, both are different. Then we cannot compare it. Only we can compare it when they have the angular. Similarly, two persons if they are running, only where only where we can compare those two persons when they are running on the same surface. అంతేగాని ఒకడు ఒక చోట పరిగెడుతుంటే మనం we cannot compare it. Both are running on the same track. When both the persons are running on the same track only we can compare. The first person is leading the second person or the second person is leading the first person. So leading or lagging concept there holds good only when they are running on the same track. Similarly, here also both the sinusoidal waveforms should have the same frequency or the same phase angle, we can say. రెండింటికి కూడా phase angle theta same గా ఉంటేనే or frequency same గా ఉంటేనే we can compare it. Now is it clear? Now, then important concept here is the phasors. So every sinusoidal waveform, mathematically I already told you, a sinusoidal waveform is in the trigonometric expression is represented as V is equal to Vm sin omega theta or like this. So the trigonometric expression of a sinusoidal waveform you have seen V is equal to Vp sin theta or Vm sin omega t, whatever it is, like this. This type of expression representing the sinusoidal waveform we called as a trigonometric expression of a sinusoidal waveform. And a sinusoidal waveform can also be represented. A sinusoidal waveform can also be represented in the phasors. So a sine wave can be represented either as the projection of the vector rotating at a constant rate. This rotating vector is called as phasor. Vector you might be knowing. So a vector, mathematics lo chadive unnaru, vector is nothing but a straight line. Vector is nothing but a straight line with some magnitude and direction. And if you consider a vector rotating with a constant rate of speed, and that vector is called as a phasor. That is the difference between the vector and the phasor of the sinusoidal waveform. So vector generally we call it as a straight line. This is a vector is a straight line like this with constant magnitude and direction. Direction is oriented like this. But the same vector, this is called as a vector. And but the same vector, if it is rotating, moving like this, either in the clockwise or in the counterclockwise direction, like anything, and that we call as the phasor. Therefore, a sinusoidal waveform can be represented as a phasor. That is, the every instant value of the sinusoidal waveform is represented as a phasor. Right? How? See here, if you look at the sinusoidal waveform here, the sinusoidal waveform is starting here 0, right, and increasing here and attains maximum, and decreasing here and it comes to 0 at 180 degrees, and once again increasing negatively and comes to 0 here. So if you look at the one complete cycle of your sinusoidal waveform, and that one complete sinusoidal waveform can be represented as a vector rotating in counterclockwise direction like this. So this is a vector, right? So when this vector is representing here, what is the value of sinusoidal voltage? 0 volts at 0 degrees. So if you take this vector, if you move to here, then what is the position of this vector? The position of the vector is 90 degrees. Therefore, at 90 degrees, at 90 degrees, what is the voltage here? At 90 degrees, voltage is maximum. See here, this is maximum. Just a moment. So at 90 degrees, so you got a maximum value. That is, if it is a voltage waveform, it is Vm. That is, this is Vm. So if your vector is rotated from here to here after 90 degrees, the sinusoidal waveform also attains maximum. Now, if you still rotate your vector here or your phasor in another 90 degrees, it will reach to the 180 degrees. That is, if you come to the 180 degrees, what is your sinusoidal waveform? Once again, it comes to 0. That is, here also it is in the almost 0 axis. Is it right? On 180 degrees is also similar to, is equal to 0 degrees axis only, right? Now, if you still further rotate your phasor to another 90 degrees, and this will becomes 270. ఇక్కడ sinusoidal waveform కూడా చూస్తే 270 దగ్గర రాగానే what is the voltage here? The voltage here, it is negative Vm. And here also see here it is negative Vm only. ఎందుకు చూడండి ఇక్కడ నెగటివ్ పోర్షన్ లోకి వచ్చింది, కిందకి వచ్చింది. ఇందాక ఇదేమో ప్లస్ Vm, ఇది నెగటివ్ Vm వచ్చింది. And if you still rotate your phasor to another 90 degrees, and once again it comes to 360 degrees here. Therefore, your sinusoidal waveforms also comes to 360 degrees here, right? Which is almost equal to 0 degrees point also. So now if you look at that, your sinusoidal waveform, when it completes one cycle, your vector or phasor completes one revolution. Circularly, when it is moving in the counterclockwise direction, it is completing one revolution completely. So therefore, a sinusoidal waveform can be represented as a phasor or a vector rotating in the counterclockwise direction. This is we called as the phasor expression of a sinusoidal waveform. And if at any point of time, the advantage of using this phasor is at any point of time, the instantaneous value of this phasor can be determined by finding its projection on the y-axis. The projection of a vector on the y-axis will always gives you its magnitude. So see here, suppose you take this phasor at this position. So phasor at this position is suppose this is an angle 60 degrees. Let it be 60 degrees angle the phasor. So the phasor at 60 degrees degree, what is the, it is 60 degrees. So the voltage here is this at 60 degrees. Then what is the voltage here? It is, this is the voltage. How do I write this voltage? This I can write it as, if you look at that, this is a right angle triangle. And what is this? I can write this as, this I can write it as, suppose the length of this vector is Vp or Vm. Length of the vector is Vm, if I say. So this is Vm. Therefore, what I will get here, it is the voltage at 60 degrees, V of 60 degrees is given by Vm sin 60 degrees. ఎందుకు ఇది రైట్ యాంగిల్ ట్రయాంగిల్ కదా, దిస్ ఇస్ రైట్ యాంగిల్ ట్రయాంగిల్. ఈ రైట్ యాంగిల్ ట్రయాంగిల్ లో ఇది 60 degrees కదా, దీన్ని బట్టి ఇది కెన్ ఐ రైట్ దిస్ వన్. సో వాట్ ఈస్ దిస్ ఆపోజిట్ సైడ్, ఈ రైట్ యాంగిల్ ట్రయాంగిల్ లో ఇది దిస్, దీనికి వాట్ ఈస్ వాల్యూ ఆఫ్ దిస్ ఈస్ సేమ్ యాజ్ దిస్, and that is given by that. That is, at any point of time, your phasor represent the instantaneous value. What is V60? V60 is nothing but the instantaneous value. So your phasor can be represented by a sinusoidal waveform can be represented into a phasor very conveniently to easily represent your sinusoidal waveform. See here, నేను ఇప్పుడు చెప్పిందే అది రైట్. ఆ తీటా బట్టి ఇప్పుడు దీన్ని మనం ఆపోజిట్ సైడ్ కదా, ఆపోజిట్ సైడ్ ఇందాక మనం చేసిన ఎక్స్ప్రెషన్ లో this is theta, right? This is theta, and this is hypotenuse is Vm. This is Vm, and this is V, right? So this V is equal to Vm sin of theta, right? So now can I write like this? So that means the phasor, this phasor, a phasor with an angle theta always represent a sinusoidal expression like this. Now, what is the advantage of using the phasors? So మనం ఇందాక phase shift అనేది మనం మాట్లాడుకున్నాం. So phase shift can be easily be determined by using the phasors. Phase shift, positive phase shift, negative phase shift అనేది wave forms లో చూసినప్పుడు you may get confused. కొంత కన్ఫ్యూజన్ వస్తుంది, ఏది పాజిటివ్ గా ఉంది, ఏది నెగిటివ్ గా ఉంది. కానీ when you represent the sinusoidal waveform in the phasors, then it is very easy to find the your phase shifts. So here, the position of a phasor at any instant can be expressed as a positive angle measured counterclockwise direction from 0 degrees or as a negative angle equal to theta minus 360 degrees. ఇది మాత్రం చాలా జాగ్రత్తగా గుర్తుపెట్టుకోవాలి. ఎప్పుడు కూడా అది యాంగిల్ ఆఫ్ ఫేజర్ మనం పాజిటివ్ యాంగిల్ ఎప్పుడు కూడా కౌంటర్ క్లాక్ వైజ్ డైరెక్షన్లోనే తీసుకోవాలి. అంటే ఇప్పుడు సపోజ్ ఈ ఫేజర్ ఉందనుకోండి, ఈ ఫేజర్ యొక్క యాంగిల్ మనం చెప్పామనుకోండి, పాజిటివ్ యాంగిల్ చెప్పాలి అని అంటే కౌంటర్ క్లాక్ వైజ్ డైరెక్షన్లో దిస్ ఇస్ తీటా, ఇక్కడ నుంచి ఇక్కడ వరకు అది పాజిటివ్ తీటా. అలాగే అది నెగిటివ్ యాంగిల్ చెప్పాలనుకోండి, రిఫరెన్స్ ఇది కదా, జీరో రిఫరెన్స్ కదా, రైట్. నెగిటివ్ యాంగిల్ చెప్పాలనుకోండి, ఇక్కడ నుంచి చెప్పాలి కదా. సో నెగిటివ్ యాంగిల్ ఈస్ ఈ రిఫరెన్స్ నుంచి ఇక్కడికి చెప్పాలి, వెనక్కి కదా, ఇది క్లాక్ వైజ్ డైరెక్షన్. ఈ క్లాక్ వైజ్ డైరెక్షన్లో చెప్పాలంటే నెగిటివ్ యాంగిల్ తీటా minus 360 కింద చెప్పాలి. దిస్ ఈస్ వెరీ ఇంపార్టెంట్ వైల్ యు ఆర్ ఫైండింగ్ ది ఫేజర్స్. అండ్ నాట్ ఓన్లీ దాట్, నేను ఇందాక చెప్పినట్టుగా ఫేజర్స్ ఫేజ్ షిఫ్ట్ తెలిస్తే మనకి ఏంటంటే, సపోజ్ ఇఫ్ దేర్ ఆర్ టూ ఫేజర్స్ హియర్, వన్ ఫేజర్ ఈస్ డైరెక్టెడ్ లైక్ దిస్ ఈస్ V1 అనుకోండి, ఒక వోల్టేజ్ ఫేజర్, and you have one more vector, one more phasor, one more vector is I1 here with an angle of theta. Then we can say that, see here, already we have discussed that phasors always move or rotate in the counterclockwise direction, and when we want to represent the angular measurement, you should take the angular measurement in the counterclockwise direction. And counterclockwise direction, no, theta is positive here, right, plus theta. So now if you look at that, this is counterclockwise direction, ila move avutundi. Both vectors are rotating in this counterclockwise direction. Both are rotating. But now, if you look at that in this direction, in counterclockwise direction, V1 is ahead of I. Therefore, I say this ahead of I say is V is leading. V is leading with an angle of theta. Or in other words, I can also say in other words, I is behind V. I V కి వెనకాల ఉంది అర్థం. దాన్ని I can write in our circuit terminology, I lags or lagging behind V, or lagging అన్న పర్వాలేదు. So this is the concept of lagging and leading, or phase shift, positive phase shift and negative phase shift of the voltage and current or the vectors. So it's very simple or easy way to express the concept of phasors when we want to represent the sinusoidal waveform in the phasor. Now if you